We'll solve our next system of equations by using matrices. In this case, we have a system in which we have fewer equations than variables. We have 3 variables, but only 2 equations. But we'll go ahead and we'll start by putting them into an augmented matrix. So when we do that, I'll have x coefficients of 1 and 2, the y coefficients of -2 and -1, and the z coefficients of 1 and -1, and my right-hand side constants 2 and 1. Now the idea is going to be that we start with a 1 in row 1, column 1, and we get a 0 underneath, and we go along the main diagonal and get a 1 in row 2, column 2. But in this case, that's where we'll stop, and we'll start a new process after that. So, because we have our 1 already in row 1, column 1, the next thing to do is to change this 2 into a 0. We can do this with some of our elementary row operations. We can use this 1 right above it to help us. We'll multiply this 1 by a -2, and we'll add it to row 2. And we'll do that with each element in row 1. So let's write that down. Remember, as I perform this operation, I'm not changing row 1. Row 1 stays the same. 1, -2, 1, 2. What I am changing are the elements in row 2. I'm taking -2 times row 1, and I'm adding it to row 2. So let's do that. -2 times 1 is -2, plus 2 gives me 0. -2 times -2 is 4, plus -1 gives me 3. -2 times 1 is -2, plus -1 is -3. And finally, -2 times 2 is -4, plus 1 gives me -3. Now the next step is to go along the main diagonal where I see this 3, and I want to get that element to be a 1. I can easily do that by multiplying each element in row 2 by its reciprocal 1/3. So again, I'm not going to change row number 1. 1, -2, 1, 2. I'm going to write down the elementary row operation that I'm performing outside of row 2. I'm taking each element in row 2 and I'm multiplying it by 1/3. So 1/3 times 0 is still 0. 1/3 times 3 is 1. 1/3 times -3 is -1. And again, 1/3 times -3 is -1. Now in this case, let's write down what this augmented matrix means. It really means this first row is x minus 2y plus 1 is equal, plus 1z rather, is equal to 2. And the second row means 0x, so I don't need to write that down, plus 1y minus 1z is equal to -1. And I'm going to call the first one, just for the moment, equation 1. And the second one, I'll call it equation 2. So I've rewritten equation 1 and equation 2 down. Now, what we want to do is to take equation 1 to start off with. Actually, let's take equation 2, since it's a simpler equation. Let's start with equation 2. Y minus z is equal to -1. The idea is to put everything in terms of z, because z is dependent on both equations. So let's go ahead and solve this for z, and when I do, I just move the negative z over and I get y is equal to z minus 1. Now we'll move on to equation 1. And we'll solve for x in terms of z. So we have x minus 2 times y, but we know that y is equal to z minus 1. so we'll substitute z minus 1 in there for y. And then we still have plus z is equal to 2. Let's distribute. X minus 2z plus 2 plus z is equal to 2. So we have x minus 2z plus z gives me minus z plus 2 is equal to 2. Now notice, if we subtract 2 from both sides of the equation, we just end up with x minus z is equal to 0. And if we move the z over, we get x is equal to positive z. Now we're ready to actually write our solution. So here's how we can write it. For any arbitrary choice of z, we can say that our solution set is the ordered triple where x is equal to z, y is equal to z minus 1, and z is equal to z itself. So there are actually an infinite number of solutions, and we could come up with any number of them. It's not necessary to do that at this point, but in case you're wondering, I'll come up with just one solution for you. For example, say we just let z equal 2. Well, then one possible solution would be the ordered triple. Since z is equal to 2, I substitute 2 in where I see a z. Again, I substitute 2 in for z, so 2 minus 1 gives me 1. And again, I substitute 2 in for z. This is just one possible of an infinite number of solutions for this system of equations.